Assalamualaikum and a very good day to all. Okay, today we will continue our lesson on topic transformers and couple circuits. So in this topic, we will look into the ideal model of the iron core transformers, the reflector impedance, the application of the transformers, magnetically coupled circuits with sinusoidal excitation, and also the coupled impedance. So for the first one, we will look into introduction for the ideal model of the transformer. Okay, transformer is actually a magnetically coupled circuit which has three main parts. Okay, the first part is the core, which the winding are one, and then it has two windings here. Okay, the first winding and this one the second winding, which behave as an inductor for the circuit. Okay, coupling meaning that the magnetic field in one circuit induce voltage in another. Okay, so how the transformer works? When the alternating current flow through any of the windings, flux will produce surrounding the windings. So the magnitude of this flux is proportional to the magnitude of the current flowing through the windings. Okay, since alternating current produce alternating flux, so self-induced EMF will be produced across the winding. Okay, this induced voltage is in opposite polarity of the source. Okay, so for this one, you have to recall back the Faraday's law of electromagnetic induction theory. Now we go to the another winding of the transformer. Okay, since the second winding is attached to the core, so the second winding will get skinned with the varying flux from the first winding. Okay, so due to the varying flux linkage of the first winding, there is also self-induced EMF produced in the second winding. The EMF produced depends on the number of the coils in the winding. Okay, then if we connect a load across the second winding, the current will flow through the circuit. So we have seen that there is some portion of the input power is transformed to the output in the second winding. Next, we move to transformer construction. Okay, transformers can be categorized into two types, which is iron core transformer, and the second one is the air core transformer. Okay, for the iron core transformers, it is generally used for low frequency application such as audio and power. Iron core provides an easy path for magnetic flux. Okay, because the flux is flowing through the core. Okay, the second type is air core and ferrite core types. Okay, for the air core, it is used for high frequency applications such as radio frequencies, and for the ferrite, it increases coupling between cores while maintaining lower losses than iron. Winding directions. Generally, when we study about transformer, we assume that the primary and secondary voltage and current are in phase, but such is not always the case. In transformer, the phase relation between primary and secondary currents and voltage depend on how each winding is wrapped around the core. Okay, refer to this figure. Okay, you may see that the primary side of both transformers are identical. Okay, so we can see this part is identical with this figure. Okay, whereby the primary windings of both transformers are wrapped in the same direction around the core. Okay, but in the second figure, you may notice that the secondary winding is wound around the core in the opposite direction from the secondary winding in the first figure. Consequently, the voltage induced in the secondary winding in the second figure is 180 degrees out of phase as compared with the induced voltage in the secondary winding in figure 1. And the direction of the secondary currents is opposite from the primary current. Next, we move to tightly coupled and loosely coupled circuits. If most of the flux produced by one of the coils links the others, coils are tightly coupled, otherwise it is loosely coupled. All transformers operation are described by Faraday's law. Okay, in Faraday's law, the voltage induced in a circuit by a changing magnetic field, okay, it is equal to the rate of the change of flux linkage. Okay, result from the Faraday's law different from iron core and air core transformers. Iron core characterized by turn ratio, okay, air core characterized by self and mutual inductance. The ideal model of the iron core transformer. Okay, it is the ideal transformer which neglect the loss effects, which is typically small. So this is the figure for ideal transformer. All the flux is confined to the core and links both windings. Okay, this is called tightly coupled transformer. Next is voltage ratio. Okay, this equation is the equation for the primary winding of an ideal transformer, and this equation is used to calculate the voltage induced, which is EMF, in the secondary winding of the ideal transformer. From both equations shown here, the induced voltage is equal to the rate of change of magnetic flux multiplied with the number of loops in the primary windings. And for the second equation, the EMF is equal to the number of loops for the secondary winding multiplied with the rate of change of magnetic flux in the secondary winding. Simplified from both equations as shown in the previous slide, okay, the turns ratio A is equal to the voltage induced in primary windings divided by the voltage induced in the secondary winding. Okay, it is equal with the number of loops in the primary windings divided by the number of loops in the secondary winding. Okay, relative polarity determined by direction of core windings. Okay, as you know, transformers are the device which are used to decrease or increase voltage produced by the electric generator. So there are two types of transformer, which is step up transformer and step down transformer. Okay, for the step up transformer, the secondary voltage is higher than the primary voltage. So here the voltage ratio is less than 1. Okay, for the step down transformer, the secondary voltage is lower compared to the primary voltage. So the voltage ratio is greater than 1. Okay, we also have current ratio for the ideal transformer. So when the power in is equal to the power out, the efficiency is said to be 100%. And the current ratio given by the induced voltage for the primary windings multiplied with the current in the primary windings is equal to the induced voltage in the secondary winding multiplied with the current in the secondary winding. So when we rearrange this equation, we get the current in the primary winding divided by the current in the secondary winding is equal to the induced voltage in the secondary winding divided by the induced voltage in the primary winding, which is equal to 1/2.